This is the typical kind of example we want to be able to start addressing by the end of today's class. It says let S be equal to the upside down bowl for Z is bigger than or equal to 0. It says oriented in the positive Z direction. All that means is that when we look at the upside down bowl, we all agree that positive is this direction. So if we're going to measure flux, we want to know basically how much stuff is actually coming through and up the bowl and not down and inside the bowl. Okay, what is the flux of? And they give us a vector field. Remember, that's actually the vector R, so it actually sticks directly out through S. We have two problems. Number one, S is curved, and number two, F is changing. And so what we're going to do is we're going to do the calculus thing, is we're going to zoom in on one part of the graph until it looks flat, and we'll just discuss that in just a second. And so close that all the vectors that actually are very close to that point almost all look the same. Then we're actually going to be able to use the formula we got before, where we take the vector and we dot it with the unit normal, and then we multiply by the area. So what we're going to do is we're going to try to find a formula for what happens when we zoom in. So we're going to blow this picture up as big as I can get here, I think. So what we're going to do is just get this picture as big as I can get it, like this. Alright, so this is coming down like this. A little more. Goes over like this and goes over like this. Yes. And what I'm going to do is put a little rectangle right down there. And then I'm going to go directly above it. And what you're going to get up here is going to be a little parallelogram. So this is going to come down like this, come down like this, come down like this, come down like this. Now it might seem a little bit strange at this point to draw the rectangle down here first, but that way this is delta x, this is delta y. We can certainly cover this entire bowl with those kinds of patches because all of them project straight down to such a patch. And what we want to do is find a vector that's perpendicular to this, that points directly out and whose area is equal to the area of that little patch. That is not only just cross product, this is one of the reasons cross product was invented, was to do exactly this task. What I'm going to do is start assigning coordinates. What do I need here? In general, I like to have a formula. We do have a specific formula for that, but at the moment I'm just going to say I want z equals f of x, y, like that. And I'm going to call this little corner down here in the plane xy like that. That way the coordinates up here are going to be x, y, and then f of x, y. The coordinates right here are going to be x plus delta x, y, f of x plus delta x, y, like that. And the coordinates right here are going to be x, y plus delta y, f of x, y plus delta y. And why do I need those? Well, cross product finds a vector that's perpendicular to given vectors, so I want this little vector here, which I guess I'll call u before I calculate it, and this little vector here, which I'll call v before I calculate it. Now vector u starts at the point xy, f of xy, and ends at the point x plus delta xy, f of x plus delta xy. And so we can write down exactly what u is. It's going to be, let's see, x plus delta x minus x is going to be delta x. Y minus y is 0. And then the last piece is going to be f of x plus delta x, y, minus f of xy. Just like that. And v is going to be very similar. V is going to be, let's see here, it's going to be 0, and then delta y, and then f of x, y plus delta y, like that, minus f of xy, like that. I think that's right. And what we want to do, unfortunately, is we want to take u and cross it with v in such a way that it doesn't kill us. Well, this is what we're going to do. We want delta x really, really small, so we're going to do what we did when we did Green's theorem. We're going to put a little delta x down here, and a little delta x up here like this. And then we're going to put a little delta y down here, and a little delta y up here. We're going to get rid of our picture now at the moment because I want to do that one little calculation. We're not going to do the calculus thing until the next video anyways. I want u cross v. U cross v, way up here. Now, what is u? U is delta x, 0. Now, this piece right here, that looks like a difference quotient. Since delta x is small, that looks very much like fx. So this is going to be fx at that point times delta x, and we're crossing that with 0, delta y. And I look it down here, and that looks like very much like a difference quotient where delta y is changing and delta x is, and x is not. So that looks like fy. So I'm going to come back up here, and this is going to be fy delta y like that. And we need to do the cross product. So we're just going to put it in the cross product formula that we earned by doing the distributive property so hard. So here we go. This is going to be I, j, k, and then delta x, 0, fx delta x, and this is going to be 0, delta y, fy, delta y, and now we're just going to calculate. This is going to be minus fx delta x delta y I, and then I cross this off and cross this off, and I'm going to get minus fy delta x delta y, and then I cross off this column, row in this column, and then I'm going to get plus delta x delta y. Now we can, and this is k, and this is j. Now I'm going to pull out the delta x delta y. I'm going to write the other one in what I think is easier to understand notation. So minus fx goes right here, minus fy goes right here, and 1 goes right there. And so this is actually what is going to function as our area vector. In the next little video, we'll put everything together and make sure we get an integral we can look at.